Service friends, I'm Orpheus Praxis, and welcome to my channel. Today is a special episode. We're diving into one of the simplest to state, yet most stubborn problems in all of mathematics, the Collatz Conjecture. Even school kids have heard of it. Take any natural number. If it's even, divide it by 2. If it's odd, multiply by 3 and add 1. Repeat. And here's what the conjecture claims. No matter what number you start with, you'll always end up at 1. It sounds almost like a game, and maybe that's why it's so often underestimated. But behind this innocent game lies a mathematical abyss. It was proposed by German mathematician Lothar Collatz back in 1937, almost a century ago. Since then, tens of thousands of hours, hundreds of papers, thousands of numerical checks, but no complete proof. Why? Because despite how simple the rules are, the structure they generate is unbelievably complex. The sequences jump up and down, sometimes reaching massive heights before eventually collapsing back to 1. Trying to trace the behavior of each number leads us into a tangled forest without a map. Some have called it a trap for smart people. Others, the arithmetic twin of Fermat's last theorem. The great mathematician Paul Erdos once said, "Mathematics is not yet ready for such problems." But what if the problem isn't chaos? What if the problem is how we're looking at it? What if we're not supposed to look at each path individually? That's the bold idea proposed by Preece and Bateman. They approach the Collatz conjecture not as a collection of number sequences, but as a structure. Not as chaos, but as hidden order. Self-similar, like a fractal. Their model combines two powerful tools: probabilistic analysis, where the Collatz process behaves like a kind of random dynamical system, and fractal architecture, where the entire structure is defined by scaling symmetry, even involving the golden ratio. The result, a theoretical formula: the average length of a Collatz sequence grows like log² of n ta, log² n. Not a rough estimate, but a result derived from a stochastic model embedded in a fractal level structure. And the formula? Tested on 1 trillion numbers with an impressively low error margin. But it gets even deeper. Behind this result is not just a rigorous mathematical method, but a philosophical perspective. Collatz is more than arithmetic. It's a reflection of a universal principle, complexity born from simplicity. So, is this just a beautiful theory? Or is it a real step towards solving a problem that's remained out of reach for nearly a century? That's what we're exploring today. Let's dive in.
Okay, let's unpack this one. Imagine a math problem. Seems really simple. Pick any whole number. If it's even, you just have it. If it's odd, multiply by 3 and add 1. Now, the Collatz conjecture, it basically says no matter what number you start with, keep applying these rules, you will always eventually hit the number 1. Sounds almost like a kid's game, doesn't it? But for decades, this little puzzle, it stumped some of the smartest people out there. No proof.
Yeah.
So what if, just what if, someone's finally cracked it? That's what we're diving into today. There's this really interesting paper, Proof of the Collatz Conjecture, Fractal Approach and Asymptotic Verification. It's by Andre Preece and Boris Batnin.
Yeah, and our goal here is to really get into their approach. It's quite novel. They combine probabilistic analysis with this idea of a fractal level structure.
Mm-hmm.
And they use that to propose, well, a full mathematical proof. It's a completely fresh angle on a notoriously stubborn problem.
It really is amazing, isn't it? The rule itself is so straightforward, you can explain it in seconds, yet proving it works for every number. That's where the mystery lies. Decades of searching for some kind of pattern, and this is where Preece and Batnin come in with something, well, pretty radical.
Exactly. What's really fascinating is they argue the process, the sequence of numbers you get, it isn't just random jumping around. They say it actually shows a self-similar structure, like a fractal. So they describe it using what they call a fractal level system. Think of like you zoom in, you see similar patterns repeating. They found this underlying order where, honestly, most just saw chaos before.
Okay, a fractal structure. That's a big conceptual leap, right? Seeing order in that randomness. But how do you get from seeing a pattern, like a fractal, to a solid mathematical proof? I mean, a pattern is one thing, but proving it holds for all numbers, forever.
That's a really good question. So they didn't just stop at observing the pattern. They built a mathematical model. They treated the Collatz process like a random process with defined probabilities. So like a 50-50 chance at each step. Either you divide by 2 if it's even, or you do the $3 plus 100 thing if it's odd.
Mm.
right? P even is half, P odd is half.
Okay, so they turned it into probabilities.
Yeah, and that allowed them to use something called a recurrence relation. It's basically a formula that links the average sequence length for a number n to the average lengths for the numbers it might turn into next, like n2 or 3n plus 1. It lets you sort of map out the average behavior step by step.
Right, I see. So using that relation, what did they find? Especially for, really, really huge numbers, that's always been the tricky part.
Well, that's the core of it. They analyze how this relation behaves asymptotically, meaning for incredibly large n. And the big reveal was this. The average length of a Collatz sequence, Tn, follows a very specific mathematical law. It grows as logarithm squared of n. So Tn, quadratic logarithmic growth.
Quadratic logarithmic growth. Okay, so what does that actually mean for the conjecture? Why is finding this average behavior such a breakthrough? It sounds predictable, which Collatz usually isn't.
It means that even though individual paths, for specific numbers, can look totally wild and unpredictable,
Yeah.
the average journey towards one across all numbers is actually quite, tame and predictable. It grows slowly, logarithmically. It suggests there's this deep underlying mathematical structure governing the whole thing. It's not just random chaos. If you connect that to the big picture, it implies the process is stable, it doesn't run off to infinity on average, it pulls towards one.
Wow, okay. That's powerful. But theory is one thing. Did they actually test this against real numbers, like lots of them?
Oh, absolutely. They didn't just leave it as theory, they ran massive numerical experiments.
Mm-hmm.
We're talking a sample size of 10, 12, that's a trillion starting numbers, a huge
A
computation.
trillion. Okay, that's serious testing.
And the results. They found strong consistency between their log² prediction and what they actually saw in the data. The average error between their predicted sequence length and the real length was tiny, just 1.23 steps, with the standard deviation also really small, 0.98. They even showed graphs comparing theory and data, and the match is very convincing.
So it wasn't just elegant math, it actually matched reality, even under that kind of intense numerical pressure. That's pretty significant validation. So wrapping this up then, it sounds like we've seen a really major step here. Maybe not the final word yet, but a proven law for the average sequence length, confirmation of this underlying fractal idea. It's huge for Collatz.
Definitely a huge leap. And it naturally raised the question, what's next? The authors themselves point to future research directions, things like refining the model, especially for even larger numbers, maybe digging deeper into the properties of this fractal structure they found. And they even mentioned looking for links between Collatz and maybe quantum systems or other dynamical systems.
So, yeah, more work to do, but this is a landmark paper. It really feels like one. So here's a thought to leave you with. What stands out most to you from this steep dive? And maybe think about this. How many other math problems, these long-standing mysteries, might just be hiding these beautiful, unexpected structures, kind of like this fractal pattern in Collatz, just waiting for someone to find the right lens to see them? That's a beautiful thought to end on. Sometimes it's not the complexity of the problem, but the simplicity we haven't yet recognized, or the structure we haven't yet noticed. Maybe the real shift isn't in new equations, but in new perspectives. Thanks for being part of this exploration. If this paper is any sign, the Collatz conjecture may be less of a dead end and more of a doorway. See you in the next one, and until then, keep thinking deeply. Subscribe to stay with us on the path. I'm Orpheus Praxis, wishing you clarity. Namaste.